Okay, off we go. By the way, I think that the problem with my laptop, not the audio not working correctly, I think that's resolved. It seems to have been anyway. A recent recording, I went to the YouTube channel and listened to it and didn't see any audio problems. So, okay, cool. So anyway, mysteriously, whatever the problem was with the laptop is resolved. Okay. All right. So here's where we were last time. We were almost here. But we could kind of summarize the last couple of pages of lecture notes by just, in some sense, this is a summary of the last couple of pages of lecture notes, which is we identified this quantity of interest called flux computed with a boundary surface integral. Keyword boundary, super important. I'll come back and pound on that point in just a minute. But this is a quantity of interest. It's a quantity computed on volumes. And so keep in mind, when I say quantity here, what I mean is you give me a set, I give you a number. Right? So you give me a, region of some sort, I return how much mass is in that region. That's a quantity called mass defined on those regions, right? So specifically, this quantity is defined on volume. You give me a three-dimensional solid region, right? And this says, okay, take that three-dimensional solid region, look at the boundary, compute the flux through that boundary, right? That's what this quantity is. Second key observation that we made, depending on how you count, it's an accumulating quantity. The whole is the sum of the parts. That's all that says right there, is that the total flux is sum of all the little bitty correspondingly computed little pieces of flux on all of the little sub-regions, the little miniature little sub-boxes that we chop our three-dimensional region up into. The whole is the sum of the parts. That's all that says. And then we talked about, because it's an accumulated quantity, there is this associated notion of density, specifically that there is this thing, this density, that if you want to know how much flux, this quantity, this stuff, right, this almost like a stuff, if you want to know how much of that there is per unit volume, well, stuff is stuff per unit volume times volume. Okay. All right. So we talked about all that last time, right? And notice that by kind of stringing together these ideas, oh my gosh, we have found ourselves a new huge theorem. This is called Gauss's divergence theorem. This is a massive theorem. This is one of the top two most important theorems for you to take away out of this course. Tremendously valuable. Arguably top one. And we're going to see a bunch of applications of this theorem today. We're going to start with a starter example, but various very cool applications are going to come out, and we'll get to that in just a few minutes. Okay, so first, just as a computational tool, tip of the iceberg. But as a computational tool, notice what this says is if you find yourself looking at a boundary flux. Again, key word, boundary. It's got to be a boundary. Very important. Again, we'll come back to that in a moment. If you want to compute a boundary flux, well, instead of the sometimes terribly inconvenient possible approach of parametrizing that boundary, computing the partials, computing the capital N, et cetera, pulling back, right, dealing with the corresponding double integral, which might involve significant effort, you may instead compute a triple integral of a completely different quantity, namely the divergence of whatever vector field whose flux you were talking about. And sometimes that divergence is just a lot easier to deal with. And likewise, sometimes the solid is much easier to deal with than its boundary. And so there is tremendous potential for this to be a computational tool. And that's the first application we're going to see of this coming up right now. Coming up in 10 seconds, do notice we have conditions. These, one of the annoying things about math is that every conclusion that you write down has conditions, right? Yes, you can draw certain conclusions, but only if certain assumptions are satisfied. So we do need the vector field to be continuously differentiable. If it's not, we've got a problem. And by the way, even so much as at a single point, even if it's just one measly, tiny, little, itty-bitty single geometric point, unacceptable. The whole theorem crashes and burns. So we'll see an example of that coming up in a minute as well. Okay, so first a little starter example. Excuse me. So we want to compute a flux. You'll notice right there, right? Surface given, vector field given, and we want to compute a flux. Okay, well, shoot, that flux is something that apparently I can turn into a triple integral. Boom! Why don't we just do that? Everybody see the allure there, right? Very tempting. When asked to compute a flux, we have a theorem about how to compute flux. Seems like a really good idea. There is a nasty problem here. You cannot apply this theorem in this case. And it's because of this boundary condition, right? It says right there, it's got to be a boundary. By the way, who cares? What, are we just being uptight about this whole boundary thing? Why is it important that it be a boundary? Look back to how we got this in the first place. Right? We only were able to make this argument about this being an accumulating quantity in the first place because of exactly how boundaries create orientations that create the cancellation that makes it all work in the first place. So if your surface is not a boundary, and keep in mind, boundary is a loaded word. Boundary means oriented in a very particular way. If you don't have a boundary, you're out of luck. You cannot use this theorem. Right? So we have to look at our surface here, our surface that we're hoping is a boundary. Right? We got to look at that surface. We got to ask, is it a boundary? And I know I'm making a big deal out of a seemingly small point, and I'm making a big deal out of this because this is so important. And I see this happen on exams so often that students will, as I was kind of casually implying with the green highlighting that a lot of students will see a flux. Oh, flux, cool, Gauss, boom, triple integral, divergence, and just proceed. And the argument doesn't hold any water. It doesn't make any sense. And it's a catastrophe on the grading, right? So I make a big deal out of it because I'm trying to reduce the occurrence of people having these exam catastrophes that I don't want y'all to have, right? So, okay. And by the way, the bigger a deal I make out of this, the less catastrophes I see. So it's a good thing. Okay, so let's ask the question, is this a boundary? And let's see here, the surface that we were given, unit sphere, wait a second, inward oriented. Now, is that a boundary? And no, very importantly, that is not a boundary. Boundaries are oriented according to very rigidly specific, arbitrary to be fair, but specific standard required conventions. And this isn't it. So we got a problem. We cannot apply Gauss's divergence theorem. Now here's the good news. Y'all will probably notice that this is a very analogous argument I'm about to make, analogous to something we did with Green's theorem, where we had something that wasn't a boundary, but we recognized, as we're about to recognize here, that there is a very closely related surface that is a boundary, right? This, what I have in blue here, the outward-oriented unit sphere, that is a boundary. And the only difference is the orientation. Right? So the beautiful little move that we make is a real easy move. The flux that we've been asked to compute relates to a flux through a boundary, for which we're very interested because we have a powerful tool for that, by way of that minus sign. That's all you got to do. That's really easy little side step of a cannonball, and I encourage y'all to be on the lookout for that. It's a really nice, easy little move. Okay, so sweet. Now that we have rephrased the question as a question about a boundary flux, go to town, right? We've got here, let's see here, I'll go ahead and do this. Now we have a flux through what is, yes, indeed, actually a boundary. All good. And so yes, wrong color. Yes, we will turn this into a triple integral over the interior, like so. Is everybody happy? Okay, it's kind of all over but the shouting at this point. Well, there's one other little slick move we're going to have to deal with. I do have to compute the divergence. We have a nice crisp formula for divergence. It ends up being 3 plus x. Make sure you can do that. Right? Easy formula. Make sure you got that formula memorized and you're proficient in computing it. And so yeah, the one last ugly little detail is how to compute this resulting triple integral. And it's not so bad. And I guess if you wanted to do this by brute force, yeah, sure, I guess you could. Spherical coordinates, natural choice, right? Wouldn't want to do this in rectangular coordinates. Yikes. But in spherical coordinates, the bounds on the unit ball are pretty easy. 3 plus x is not that bad. You write it down, you do some trig, it'd be doable. But there's a much better way to do this. The much better way to compute this integral is to recognize it as being an integral of 3 plus an integral of x. And while this initial integral doesn't have any particularly convenient properties, it's not, can't apply symmetry, it's not an integral of a constant, but these integrals over here, these do, wrong colors. You know what, let me stick with the established smiley face convention here. So these are much nicer integrals to deal with, much friendlier. Integral of 3 over the unit ball, 3 times the volume. Boom, nothing to it. No trig, no nothing. Integral of x over the unit ball, 0 by symmetry. Boom, done, right? No trig, no nothing. So I think it's a nice move you want to look out for. I encourage y'all to constantly be vigilant to look out for this. This kind of thing, again, happens, right? To be fair, yes, I manufactured this example so that this would come up, but that doesn't mean it doesn't happen naturally. It does. It 100% happens a lot in the real world. So please be on the lookout for that kind of thing. Saves you loads and loads of trouble. Personal experience is my source on that claim. Last comment, 0 by symmetry. I have deliberately left out here what y'all are going to have to include if you cite symmetry on an exam. We've talked about this long ago. You do have to say it's 0. You do have to say by symmetry, and then you also have to say through what plane in this case, or in a 2D case, through what line. So don't forget to say. By the way, think it through here. What's the plane of symmetry in this case? Make sure you're clear on that. And if you want to make sure that you got the right answer, then fill in all of the rest of the details. You don't have to do it on the exam. But again, on the exam, you do have to be right. Right? So if you want to make sure you're right, it's a good thing, right? Fill in all the rest of the details of that symmetry argument. Formula for the reflection, algebraic confirmation of oddness, etc. Okay. How we doing? Okay, so on to some physical examples. There's a bunch of cool physical examples. This is my favorite one to start with. This is also, believe it or not, this is going to be a tool that allows us to solve some really cool engineering problems. Well, physics problems, but that'll be useful to y'all in engineering because you're going to have to learn some physics if you haven't already. And so the light bulb, I think the light bulb is a lovely example. So now if you think about what a light bulb does, it makes light, okay, but more to the point, it generates photons that fly outward. Bunch of little particles flying kind of roughly all in the same direction, like a fluid. Right? So we can represent the flow of photons coming out of a light bulb with a vector field. And you may recognize this vector field. It is inverse square radial. We talked about that back in chapter 3. And we talked about some specific examples, and we're going to revisit those specific examples momentarily. Real quick little reminder, I do have to say this is what it looks like away from where the LED is. The LED at the center of the light bulb is not a point. It's not a geometric point, right? It'd be easier to deal with in some sense if it were a geometric point. It's not quite. It is teeny tiny, itty bitty, really small, sure, right? But it's not a geometric point. So if you want to talk about what the vector field is right next to the origin, like super duper, like inside of the LED, yeah, things get weird, right? We're not going to talk about that here for the moment. But anyway, away from where the LED is, everywhere else, this is what the vector field looks like. Okay. All right, so y'all can take this vector field and you can compute the divergence. It's just a calculation, right? No, not at the origin, right? At the origin, this thing blows up, right? It's undefined, total nonsense at the origin. But anywhere else, you can just straight up compute the divergence. And here's what you're going to find. You get 0. Y'all may have actually already done this calculation now. I think maybe this was a chapter 3 exercise. I don't remember. Might have been. Anyway, it's a bit of a tedious calculation, but it's very doable, and you get 0. So what does that mean, and why is that sensible? I claim this is actually sensible for a pretty simple to argue reason. If I were to think about some ball out here, far away from the origin, again, the things get weird at the origin. Let's ignore that for the moment. If I were to take some ball there, and if the claim is that the divergence is 0 everywhere inside of that ball, that would suggest that the flux through that ball must be 0. Now, what are the odds? That seems like a hard calculation. Don't I need to parameterize that sphere, right, around that ball? And isn't that going to create some trig? And this is a weird vector field. And you're telling me if I take that entire tremendous calculation and go through, everything's going to cancel? You get 0? Seems like a big ask to find this believable. Let me show you why this is obvious. This is at a glance, well, of course. And the reason why is the flux through that ball consists of photons, and keep in mind, photons are the fluid. That is the fluid. And every photon that goes in also goes out. Every contribution to positive flux is also a contribution to negative flux, and they literally straight up 100% cancel perfectly. No tedious calculation required. It's a really cool little trick to notice. Everybody see that? Everybody believe me that every photon that goes in also goes out? Very cool. Okay, so no surprise. And again, once you make this observation, once you realize the fluxes are all 0 for little balls like that, then it's a pretty easy ask that the divergence should be accepted to be 0. Okay. All right, now what's happening at the origin? Well, more to the point, where the LED is. So in this non-zero volume of, the actual tiny but non-zero physical space where the LED is, things get weird. And the divergence is huge there. And let me try to make a case for why I think this is pretty believable. And it's not that different of an argument, different details. But let's think again about a little volume. I can't make circles. Little volume like that, except instead of looking at one away from the origin there, or there, or there, or there, or there, we're going to put it right there. Now let's think about that little purple sphere. Right? So on that purple sphere, what's the flux through that sphere? It's a lot, right? There's a bunch of photons being generated by that LED, and how many of them are going through that purple sphere? All of them, right? All of them. So let's think about what the divergence would be. And again, just, sort of intuition, back of the envelope. We don't have to parameterize and do all the calculations. We have a huge amount of flux. All of the flux, the entire 1,200 lumens of flux coming out of that LED, right, in a teeny tiny, itty bitty little sphere. What is divergence? Flux per unit volume. A lot of flux, tiny volume. Tremendously huge divergence. Does that make sense? Everybody buy it? Okay. All right. Okay, so so here's one thing I really like about this example. This example is another case of what I'm going to call satisfaction to a weird point that I've been pushing on y'all, right? That I think is tremendously important to be able to kind of get the sense of how all this vector calculus stuff works. And this point is, and again, weird and a big ask, and I know it seems a little creepy, but this idea that quantities that are computed on boundaries actually come from the interior, like it's happening in the interior. We compute it on the boundary, but I'm asking you to buy that all this boundary flux that we're seeing on the boundary is actually coming from the interior. And I gave you one, I think, very satisfying example of that, which is the fundamental theorem of calculus. Change is computed by looking at the boundary points, by looking at the starting value and the ending value, and yet, of course, obviously change happens in between. Well, of course it does. That one's, again, I think an easy buy. Let's think about the claim that I'm making here. Is it that big of an ask, really, for me to claim that the flux of photons coming out of the shell of the bulb, we've got this flow of photons coming out of that shell. Is it weird for me to claim that that's coming from the interior? Not at all. That's where the LED is. Of course they're coming from the LED. That's in the interior. Right? So not that weird, right? Pretty physically natural. And again, notice that divergence points to it, right? Huge divergence is telling you, oh my gosh, that's where the fluid's coming from. That's with all this flux that we detect on the boundary. Yeah, it's coming from there. How much of the flux is coming from here or here? None is coming from there. And well, again, of course it's not coming from there. There's no LED there. That's just air. Now there's a bunch of photons there at any given moment, but they're passing through. Right? Anyone that goes out from one of those green regions came into that region from elsewhere. Okay, how we doing? Does everybody buy it? Does everybody see what a great job divergence does here at a purely algebraic tool, and it's pointing right to exactly what's happening in this scenario? All right, so this is, like I say, one of my favorite examples. It's useful in a lot of ways. Now, I do want to, before we go on, talk about singularities. And again, reminder, we do have this condition. Okay, no singularities, not kidding, right? It really messes things up. So let me show you an example of that. And keep in mind, here we were talking about an LED. LEDs, again, are very small, but they're not points. They do have a non-zero, though tiny volume. So let's think now about the limiting case of that, where LEDs get smaller and smaller and smaller and tinier, and as it approaches a no volume, can't actually make such a thing, but let's imagine, technology always makes things smaller. They'll probably come up with smaller and smaller LEDs that'll get closer and closer to no volume. And now let's consider that scenario. Well, it's still making an outward flow of fluid emanating from, let's call it a point. So it's still going to be inverse square radial. Right? Sure. Same deal. This still has the same divergence. Oh, typo. I wrote divergence is 0. It's not a vector. Sorry. Scratch off, if you would, on your notes, if you can, the little vector over the 0. The divergence is a scalar, of course. That was just silly. Let's see here. Okay, so divergence is 0, easy calculation. Now, of course, also, though, there is a singularity at the origin. Something bad's happening at the origin. The Vector field's not even defined there. Right? Okay. It's just the 1 point. One teeny weeny little bitty point. How could that matter that much? I mean, it's just the 1 point. Well, let's look at it. Let's look at Let's look at what the divergence theorem would say. So you can compute the flux, and now you can do that with a sphere. Very doable calculation. By the way, this flux calculation that I'm asking y'all to do through spheres centered at the origin, very straightforward. You can totally do it. You don't even have to bother parameterizing. There's some really nice geometric good fortune that happens. This is an excellent little exercise. I strongly encourage you to do it. The answer ends up being 4 pi k, k being the same k from the vector field. Give that a shot. Right? And again, look for the geometric good fortune. All right. By the way, this result is also true for many other surfaces, even that aren't spheres. It's harder to do the calculation. But also true, basically for any surface that surrounds the origin, you will get the same answer. Harder to show, right? But anyway, side note. So now, though, let's look at this particular one, though, and let's now try to compute the triple integral of divergence. Well, wait a minute. The divergence, our integrand, is 0 everywhere in that interior, except for that, of course, 1 point. Right? We do still have this singularity at the origin, a single point. Now, what's that integral going to be? Right? We've got an integral. Our integrand is 0 everywhere except for 1 point. Points don't have volume. Right? I mean, it's kind of hard to figure how you'd make any sense out of such an integral other than that it kind of has to be 0. And by the way, I'm sweeping some dirty business under the rug here, so that's not what this course is about. So anyway, do we get the same results here? Does the triple integral of divergence compute the boundary flux? Doesn't look like it. Right? And so what's the problem? Well, the only thing that went wrong, there's nothing wrong with this vector field at the overwhelming majority of points in the entire domain except for that one single point where, we had a problem. And again, everything goes off the rails. Everybody see what I'm talking about here? Okay. So you do have to be really careful about that. Now, here's some other facts. I keep erasing the... sorry, again, scratch that thing off. Here's another fact. If you take any surface that does not include that does not surround the origin, any boundary surface that doesn't, a boundary of a region that does not include the origin, flux will be 0. So on any surface like that purple, and by the way, obviously 0. Obviously 0 because, of course, every photon that goes in also goes out. Same argument, right? Okay, so any surface that doesn't surround the origin, we get 0. Any surface that does surround the origin, we get 4 pi k. Yeah, let's see, how am I going to do this? I'm going to say 0, 0, 4 pi k. Eventually you start to realize this, there is a method to the madness here, right? This is not completely random, and it's almost like there's a, like what I like to call a lump of flux at the origin. Let's just imagine, now keep in mind divergence is flux density. We like to think of flux as a stuff. We like to think of flux as a stuff that's distributed in some sort of continuous manner over the interior. All I'm saying here, just a little bit different, is that flux is still a stuff, And this time, it's just I'm not viewing it as being smoothly distributed. I'm viewing it flux as having a lump right there at the origin. And now let's just kind of think it through. Does everything make sense? In the green surface, what's the total amount of this stuff of flux continuously distributed by way of divergence or in lumps altogether the grand total amount of flux? Yeah, there's a lump there. We get 4 pi k. That's how much flux stuff there is inside of the green surface. How much is inside of the purple surface? None. Now everything kind of works, right? And so if you there's a lot that has to get said to make this not hand wavy, and y'all may see that in a future class. But anyway, it's just I think kind of a neat observation that even though we do have a problem with the way that they're unstated, there is kind of a way to fix it. You just have to recognize that it's as if there is a lump of flux at the singularity. And by the way, here's a pretty believable assertion. Why is there a lump of flux there? Well, flux is a measurement of what's actually coming from somewhere else. Where is all the flux coming from? It's coming from where the LED is. It's coming from the origin. So, yeah, sure. Yes, there's flux coming at the origin because that's where all the flux we measure is literally coming from. Okay, all right. Enough of that. Okay, here's another example. Totally different physical scenario. I like to think of this as a gas. It could be any fluid, but gas is a convenient metaphor. I also find it convenient to want to avoid, but where's the outside air pressure? And is this gas contained in a container? And I don't want to have to deal with that stuff. So let's imagine that we're just out in outer space somewhere and there's a big lump of gas like a nebula or something like that, right? Big lump of gas, nothing else, right? Just a big lump of gas. Okay. And now imagine that it's moving radially outward. Imagine, in other words, that the gas is kind of expanding. Right? It's getting bigger and bigger, and of course that means every particle of gas is kind of moving sort of radially outward to match that expansion. Okay. All right, so that gives you a vector field. Turns out that this is a good model for that vector field. We have to put the K in there to recognize, problems with units and stuff like that. But whatever, it's just a constant. By the way, good little exercise. Make sure you're comfortable with the idea that that's what this vector field looks like. And again, consistent with the idea of an expanding gas. Okay. And now, innocent observation. If you have a finite amount of gas, and if that gas is in a finite amount of volume, you can talk about its density, total gas per total volume. And, well, if it's expanding outward, the gas is constant, the volume is increasing, my numerator is constant, my denominator is increasing, the density is going to be decreasing. Right? All right. Okay, all right. Well, let's talk now. Imagine if I were to set up some imaginary boundary surface there. And by the way, I drew it as a sphere. It doesn't have to be, whatever. But any surface like that, boundary surface, if you want to know the flux, then you invoke Gauss's divergence theorem. You compute this divergence. By the way, totally doable. Make sure you can do this. Plug in that formula for the vector field, compute the divergence. You will get, wrong color. You will get 3K. Make sure you can do that. All you got to do, of course, is take that vector field, write it in coordinates, plug it into the standard formula for divergence. No big deal. Okay, what does that 3K mean? Is that pointing to where gas is being created? When we're talking about light bulbs, divergence was a reference to the generation of fluid. Are we generating gas here? No, we're really not. There's no gas being generated. We have a finite amount of gas. Right? So we're going to have to make a different physical interpretation of divergence in this situation because it is a physically different scenario. And not just because gas particles and light particles are not identical. That's not the point. The point is they obey fundamentally different rules. Gas, let's see here. Let me go back to here. With the light bulb, we are literally generating fluid. We are not generating any gas. That's one of the key differences. Right? Here's the other thing. As we argued, with the gas, the density is changing. Pick your point. Wherever you might want to look, the density is not constant. With the light bulb, the density is constant, no matter where you look. Pick any point, right? The number of photons per unit volume in that general vicinity doesn't change because the light bulb, it's a steady state situation. Yeah, it's flinging photons out every which way, but at any given point, there's a certain number of photons passing through, and any given moment in time, there's a certain number of photons in that area, and it's not like it's accumulating. It's not building up or anything like that. It's the photon density is constant. Right, so very different fluid, and so we have to make a different interpretation. So what are we going to do in this case? Well, all right, here's my take, and I really like the following point. Another fundamental interpretation of flux. Right? In this scenario, when I talk about flux through this surface, whatever surface that might happen to be, I drew it as a sphere, it doesn't have to be. The flux through that surface represents gas passing through that surface. Wait a second, if the gas is passing through the surface, that means that gas that was inside is going outside. That means that the total amount of gas inside the sphere is decreasing because flux is saying that flux is telling you at what rate is the mass actually leaving through that boundary surface. So the pretty clear interpretation of flux here is that it's telling you how fast the total quantity of fluid is decreasing inside of the sphere. So it's the negative rate of change of mass. Quantity, however, it depends on what that K is and how you've set up your units. But in whatever sense, I think it's convenient to think of it as mass, but in whatever sense, quantity of fluid, flux represents the negative rate of change of that. All right. Now, once we make that observation, by the way, not a big ask, I think, for me to point out that mass is a triple integral of density. We already knew that, right? And by the way, hopefully also you would buy that I can move that time derivative inside the integral, like so, right? And now, having done that, now let's compare this expression with this expression. Notice both of them are integrals over the whole volume, and they're equal, and so therefore divergence would be naturally interpreted as this. Divergence tells you the negative of the rate of change of density. Right? So we agreed at the very beginning that if you have gas and if it's expanding, then overall the density is decreasing, right? But this means that divergence is going to tell us exactly where and at what rate that density is decreasing wherever you might happen to be. And with the vector field as we set it up, and again, assuming that the fluid was moving in that exact way, it turned out that divergence was constant. And so that means that we're losing density the same everywhere on the inside. So a nice little conclusion there. Everybody good with that? By the way, here's one thing that confused me a lot when I was y'all's age. I was looking at this same stuff and say, wait a minute. But divergence, sometimes it means one thing and other times it means something else. And how do you know? And I'm sorry to say, you got to think it through every time. You have to be very clear on what are the rules of the scenario that you happen to be looking at. And you got to make sense out of it every time. Okay. So always make sure to think stuff through, make sure you understand exactly what the physical scenario is, make sure you're interpreting things as they are physically happening. Okay. All right, pausing. Questions? Everybody all right? Okay, before we go on to another really cool example, I'm going to do a sort of a unification. So we had this one physical scenario where we're generating fluid, but density is not changing. We have this other physical scenario that's kind of the exact opposite. We're not generating anything, and the density is not constant. Okay. So let's consider the scenario where maybe both things are happening at the same time. Now, this is, there's different ways to approach this. I find something satisfying about this particular point of view. This is easily quibbleable. The little scenario I'm about to describe here does sort of assume that the quantities involved are positive, and don't worry about it. Everything still works even if they're not. But somehow I find this somehow to be just more satisfying to write down the fundamental relationship we need. And it goes like this. Let's imagine that this is the universe. This is the entire, Rn I've written here. But by which I mean probably R3. We do most of our business in 3 dimensions, right? So let's say R3, whatever. And suppose I've got some surface inside of there, and of course that surface needs to be a boundary of some region. Okay, so that's our whole scenario. Why am I drawing a 3-dimensional thing as a 2-dimensional thing? And the reason why is because I like to have a visual opportunity to represent the generation of fluid. And we need that because, again, light bulbs, that's what they're doing. Light bulbs literally create fluid. So it is, forgive me the sort of the weirdness of imagining our entire 3-dimensional world as a 2-dimensional plane, but that allows me to talk about fluid generation. And when you're creating fluid, imagine it's as if that fluid is coming from outside of the universe, if you will, into the universe. And in the universe, it looks like it's just been sort of, oh my God, it just came out of nowhere. Okay. All right. So there's going to be a total rate at any given moment of how much fluid's being generated. How many lumens is your light bulb? Whatever. And here's the thing. When fluid gets generated, that fluid really has to do one of 2 different things. There's really only 2 ways to go. That fluid either leaves, which, by the way, means it's part of the boundary flux, or it doesn't leave, which means it's contributing to how much stuff is increasing in that region. Right? The stuff that leaves doesn't contribute to the quantity of stuff you have. It's not staying. It just goes. Right? It doesn't cause the total amount of stuff inside the region to change, but the stuff that stays does contribute to how much stuff is in the region, and doesn't contribute to flux. So this is a starting point for getting to an important result that we'll get to on the next page. But this is our sort of foot in the door, and again, it's just a matter of observing that when you make stuff, it either stays or it doesn't stay. And once we have that, we're actually pretty well armed to move to the next step. Everything in this equation I can think of as an integral in different ways, to be fair. But let's think about this total generation rate of fluid. Well, the stuff gets created by different amounts in different places. The light bulb example, all the generation is happening where the LED is. None of the generation is happening where the LED isn't. So, yeah, there's going to be what I'm going to call a generation rate density. And the total G, the total G is an integral of that rate density. And it's just a matter of, again, the whole is the sum of the parts. Okay. Flux, of course, the divergence theorem tells us that's a triple integral of divergence. That's just math. That's the Gauss's theorem. And then mass, of course, is an integral of density. So you write these two things down, and we're basically at our big result. This equation works as a statement about integrals, and so it should also work as a statement about integrands. If these integrals add up, then the integrands have to add up the same way. Wouldn't make any sense if they didn't. If you prefer, I could take this equation about integrals, move everything over to one side, combine into a single integral that's always 0. So the integrand would have to be 0. Same result. Anyway, get to there however you like. But that, and that must also add up in the same way. And so this is called the continuity equation. And notice it kind of combines the two different phenomena that we saw in our previous examples. It involves fluid generation, and it involves changing densities at the same time. And so this is the general rule. If you want to make sense out of divergence, this is how you make sense out of divergence. It could be involved with generation. It could be involved with changing densities. And again, you have to look at your physical scenario and make sense out of it and ask yourself, wait a minute, am I generating fluid in this scenario? And then act accordingly with the algebra, and likewise with the density. So just to sort of connect things up, when we were talking about gas, the whole point, the premise anyway, I should say, of the gas example was that we have a finite amount of gas. There is no gas being generated. That then becomes 0. And that then immediately from the continuity equation gives us the result that we found separately about the gas. On the other hand, looking at the light bulb scenario. In the light bulb scenario, how do light bulbs work? Well, light bulbs, you flip it on and it starts creating this fluid. There's this flow of fluid. Yeah, sure, but it's steady state, right? There's light bulbs up there in the ceiling. There are photons shooting out of the light bulb, shooting right through between my hands here. There's a bunch of photons in here. Am I collecting photons? No. There's always pretty much the same number of photons in here in between my hands. So in the light bulb example, because it's steady state, the density is not changing. Did I hear a question? Is everybody good? So steady state means the density is not changing, and that gives us, again, the same interpretation that we had originally of the light bulb. The divergence is telling you where stuff being generated, where is the fluid in question being generated. Instantly comes out of the continuity equation. So this is a really big deal, very cool fact to know, and that's where it comes from. Yeah? Oh, did you say one more time?
Just like what the...
Yeah, so G represents the total rate that we're creating stuff, whatever the stuff is, right? Photons, whatever, right? Maybe we're looking at, historic trends in the migration of, pythons through Florida, right? Well, there's two things to think about there. Yes, there's the movement, but then there's also, they're having python babies, right? We're literally generating pythons in Florida, right? So generation, that's the total rate over the entire whatever region. the little g is the corresponding density. It's like, okay, so yeah, right in the middle of the whatever that big swamp is, yeah, I'm guessing there's a lot of python births happening there, right? In downtown Miami, not so much, right? Does that make sense?
Yeah.
So this is just that corresponding density. Yes?
Could it also be like, just an example, like if I had a light bulb right here, and I had another source of light that was nearby?
Yeah.
Okay.
Yeah. Then there'd be density, significant photon generation density at where both of those bulbs are. Yep. Right. Okay. All right. So anyway, cool fact. Moving along, let's talk about gravity. Gravitational fields we've talked about before. By the way, you might recognize those are inverse square radial. And, so that makes a gravitational field that looks like this. And I suppose I could think about some surface here and ask, oh my gosh, I've got a surface, I've got a vector field, by the way, not a very pretty vector field, right? This vector field is, got square roots in it. Magnitudes are square roots, right? And it's being cubed in the denominator, not squared. That means there are actually going to be square roots left over. So we have an ugly vector field. By the way, that's a sphere. How do we parameterize spheres? Well, we use spherical coordinates, which turns into trig. So now we've got trig functions being plugged into a scary vector field. And if I were to ask you to compute that flux, brute force, there'd be a lot to write down, and then you might say, well, clever arguments about geometric convenience. Okay, fine. Now let's look at not a sphere. Now there is no geometric convenience. Now you've got a nightmare on your hands. How are you going to compute the grand total flux through that purple surface? Nightmare. Right? Turns out this computation is super easy, and it's super easy because of an example we've already done. And you might have even noticed. You might have noticed that this gravitational field is just like a point light source, right? Structurally, the equation for that vector field, it's there's different constants. Okay, yeah, the constants are boring, right? Multiply by a constant on both sides of the equation. Who cares? Same story. Structurally, this is just like a light bulb. So, I can pretend, right, for the purposes of the calculus. You've asked me to compute a flux through a surface of a given vector field. I can say, hey, you know what? That vector field is the same vector field I would have gotten had you asked me about light bulbs. It's the same resulting math that it would be if you had asked me about light bulbs. So I tell you what, I'm going to pretend you asked me about light bulbs. I'm going to pretend that when mass creates a gravitational field, that it's kind of like a light bulb. That, here's again a little point mass. It creates a gravitational field, a radially inverse square gravitational field surrounding it. I'm going to pretend that it's actually a little bitty light bulb that's shooting out a flow of a fluid, kind of like photons. And that, I know that seems like I'm cheating. It seems like that's against the rules. Absolutely not, right? They literally give the exact same algebra, minus the constant. It's easy to deal with. And so, yeah, sure, go ahead. In fact, here's the thing. When you're doing physics, and when there is a jaw-dropping, surprising coincidence, very often that is an indication that it's not a coincidence. Very often that's an indication that we just accidentally noticed a fundamental truth about how the physical world works. Not always, but very often. Right? So, this observation in mind, it is super tempting to say that, hey, maybe this is literally how gravity works. Maybe instead of gravity being some mysterious action at a distance force. Maybe mass is constantly, just like a light bulb, shooting out little particles called gravitons. And every time you get zapped with a graviton, that graviton says, hey, yeah, there's mass over there, gravity, look, it's the law, it's not my fault, you gotta go that way now. Maybe that's how gravity gets communicated, is by little bitty tiny particles. Right? Now, is it actually? Hard question, way above my knowledge of physics. I have heard arguments on both sides. The most persuasive arguments I've heard are that, not really. There's no. If I were a betting man, I'd be betting against. But it doesn't matter. Okay, whether this is a physical reality or not is not the point. The point is, as far as we're concerned, reality behaves as if this is true. And if reality behaves as if this is true, we can proceed on that assumption and we're going to get right answers. All right, so really neat point. We don't have to think about this as a gravity question. We can think of this as a fluid flow question, basically light bulbs. So here's the resulting computation. And I've written this as kind of a little square of equations. And let's go through these equations one at a time. First of all, momentarily ignoring these constants, it's fair. It's on both sides. It's no problem, right? But other than those constants, this says mass is a triple integral of density, right? Old news. We already knew that. Why did I multiply by a constant on both sides? You'll see in a second. Okay. First thing I'm going to say about the flux. If you ask me where the flux, how much flux do I have? Well, there's mass on the inside in there. Mass is creating a flow of gravitons, let's just say. Again, who knows? Might not be true. Might as well be, though. If you've got mass on the inside and it's shooting out gravitons, how many of those gravitons are going to pass through my surface? How many of those gravitons are going to create flux as they pass through that surface? All of them. Just like light bulbs. Same story. So, more mass means more flux. Just like if I were to say, more light bulbs, more lumens on my light bulbs means more flux of photons. Well, of course. Right? So this claim right here is really just this innocent observation that mass creates mass creates gravitons. Gravitons are flux. So they're proportional. More mass, more flux. And that's why I put this constant in here on both sides. Again, got to be legal. It's on both sides. I put that in there because there is a constant of proportionality that makes this green equation work, and it happens to be that constant right there. Don't worry about those details. Okay, it's all over but the shouting. We saw why this is true. No big. We saw why this is true. Thank you, graviton metaphor. True or otherwise, doesn't matter. And we write down the divergence theorem and we make our usual little observation that if these two integrals are equal, then that must mean that their integrands are equal. And that gives us a really powerful conclusion, a shockingly convenient conclusion that you can compute the divergence of a gravitational field just by looking at the mass density. And by the way, what's really cool about this is that it doesn't matter where the mass is. If you're talking about, maybe all the mass is at the origin, okay, I suppose. But how about this? What if some of the mass was over here? Or, some of the mass was over there. Maybe more mass is over here. And maybe just a little bit of mass over there. The argument still works. Mass is an integral of density. How many of the gravitons created flow out through the surface and make flux? Well, all of them. Doesn't matter where they are. Doesn't matter how that mass is distributed. Right? So this works no matter what. And the really interesting thing is if you were to ask, now again, without the graviton metaphor, right? Without these without the divergence theorem, right? And being able to connect divergence to flux and flux to mass, etc. Powerful ideas we're invoking there. If we didn't have that, how would I compute this divergence? Oh my gosh, this would be brutal. Every single little particle of mass, that one doesn't show up well. Every single particle of mass, like this little red particle right there, that one little red particle, that creates its own gravitational field that's ugly to write down. Every other little piece of mass creates its own gravitational field that's hard to write down in a different way because it's at a different location. We would have this, oh golly, kind of infinitely many different gravitational fields that we'd have to be looking at all at the same time. And you're telling me you want me to take that gigantic monster gravitational field and you want me to compute the divergence of it? It's overwhelming. How could we do this? Much cooler to make this graviton metaphor and say, oh yeah, you know what? That it turns out it's just proportional to mass density. End of story. Powerful ideas. Everybody see that? Really cool stuff. Okay. All right. By the way, let me not get ahead of myself. Okay. So here's a valid complaint that a student could make at a time like this, which is, all right, look, that's fascinating and all, but I'm an engineer. I have no intentions of becoming a astrophysicist, and I have no intention of becoming an astronaut. Right? And so to me, gravity is a constant. I'm going to live my entire life on the surface of the earth. I'm not going to work for the aerospace industry. Gravity is a constant. I have no use for any of this. And that's a reasonable complaint if that's the only purpose this example served, but it's not. This is a lead-in to a much more important example. Something y'all do need to know. Every engineer needs to know about electric fields. Right? Kind of a big deal, right? Pretty much any kind of engineering you go into, I mean, I suppose maybe if you're going to try to increase the efficiency of gasoline engines and want nothing to do with electronics, okay, I guess maybe you don't need to know electric fields, but that's a very narrow niche. Practically all engineers need to understand electric fields. And here's the big deal, the big point. Electric fields, they're also inverse square radial. They're structurally the same as gravitational fields. And this is something I noticed when I was y'all's age, and it occurred to me, oh my God, that's a really convenient little connection. Electric fields are just like gravitational fields. When I'm dealing with electric fields, in my mind, I'm like, you know what, that electric field, it's basically a little kind of sort of a gravitational field. It's just that charge plays the role of mass. Other than that, kind of the same thing. And there's, plus and minus with charges and, repulsive forces and attractive forces. Yeah, that's just constants. That's easy to deal with. Electric fields are basically like gravitational fields. So where's the win in that? Well, there's arguably two wins. One is that I have better intuition for gravity than I do for electricity. And I'll bet you do too. We experience gravity every day, right? I mean, this is a pretty old concept. You don't get to be very old on this planet without noticing that gravity is a thing, right? It's obvious, right? Viscerally experienced every day. Electricity and electric fields are so subtle and hard to relate to, humans didn't even notice them until, like a couple hundred years ago. It was a very recent observation. It's not intuitively relatable. So I think that's a really cool point. Being able to take something abstruse and unrelatable like an electric field and be like, you know what, it's basically gravity. Very helpful. And the other point to this is that this graviton metaphor is what allowed us to relate this back to, that's farther back than I thought, to light bulbs. Right? And so connecting those two observations allows you to take the point of view that this argument, and now this is morally equivalent to what I wrote down above, same argument. It's just that now charge is an integral of charge density. Let me do this better. Charge is an integral of charge density. Now it's charge, not mass, that's creating, again, a possibly fictional, but might as well be real. Possibly charge is creating this kind of fluid of electric field fluid, whatever that would be, right? Doesn't matter what it is. But it's like charge creates this fluid, and that fluid creates flux. And so you get this same result out of the same basic metaphor. Right? And by the way, y'all may recognize that equation. That's called Maxwell's first equation. That's the way I like to number them. And then by the way, this same result over here, that electric divergence is proportional to charge density, also called Maxwell's first equation. It kind of rolls off the tongue very nicely. Here's the way I like to think about it. You look at these two equations. This first one says flux is proportional to charge. The second one says flux density is proportional to charge density. They're practically the same statement. One of them is a density statement, one of them is a global statement. But I mean, whatever, right? One of these statements is just an integral of the other. So they're practically identical. So I think that's a pretty neat observation. And by the way, who gets the credit for making it clear that statements about flux and divergence and charge and the distribution of charge are all connected? Where does that ultimately, who gets the point for that? And I missed the thing. I would give the point to the divergence theorem. The divergence theorem is the thing that makes that connection possible. So really, really important to understand the divergence theorem. If you want to have a good understanding of electric fields, you got to. It's just right there. Everybody seeing that? All right. So hope that's helpful to y'all in your physics classes, your possibly future physics classes, hopefully future physics classes. It's a tremendous advantage to study E&M already understanding stuff like the divergence theorem. Just tremendously helpful. So if you've already taken physics, here's what it would have been nice if you had known back then. And if you're going to be taking physics soon, this is going to make a big deal. Okay. All right. Okay. Off we go. So next part of the huge section we're going through, right? I think I made the observation before that section 7.3 is a monster. It's gigantic. It should be at least 2. I would propose 3 separate sections. Whatever, doesn't matter. It's just bookkeeping. But immense section. Effectively now on to a new topic. It's called Stokes' theorem, and y'all know the routine here. We've been down this road a bunch of times. First of all, we talk about boundaries, and we set orientation standards. And then we're going to observe an accumulating quantity. And then we're going to celebrate the fact that accumulating quantities behave like stuff that's actually distributed through the interior. And when you have stuff that's distributed, you can talk about the corresponding density. And once you have it as a density, then you can write stuff as an integral of density of the stuff, and there you have a theorem. I mean, I'm going to go through this in more detail, right? But, I mean, I hope that the roadmap here is kind of exactly what you were expecting. It's really structurally the same roadmap as every other theorem that every one of these accumulation theorems, boundary theorems, density theorems, whatever you want to call them. We've been down this road many times. Okay. All right. So, let's hit some details here. Okay, we're going to need to talk about oriented surfaces. Got some surface, right? A piece of paper, for example, is a surface. It might be sitting up in space like this, right? But it's a two-dimensional thing, and it's a surface. And the boundary of that two-dimensional surface is the edge. Wherever The way I like to say it is, imagine that there's an ant crawling around on this surface. The boundary is where the ant gets confused. Right? The ant's walking along, happy as a lark, no problem, boom, boom, everything's fine until the ant gets over to here and is like, oh my gosh, what happened? There's no more, the world ended. What do I do? Right? So that is called the boundary of the surface. And that boundary is a curve. Like so. And now keeping in mind that my surface is an oriented surface, that means that when you're at some point on your surface, there is an orientation vector describing what's the positive direction through the surface, right? That's what an oriented surface is. And the question we have is, okay, the boundary, how should that be oriented? Which way along that boundary curve should I call the positive direction along that oriented boundary curve? I got to pick one, right? Now, again, it's tempting to say, well, always go to the left, always go to the right, always go up, always go down. Always go clockwise is a popular sort of like take on it. And there's just problems with all these points of view. And let me address the clockwise one, right? So you look at my finger going around in a circle here. Right? Now, is my finger going around clockwise or counterclockwise? Well, from where you're standing, it probably looks counterclockwise. From where I'm standing, it looks clockwise. Right? See, counterclockwise, clockwise. Right? So, clockwise doesn't even make any sense. If you're in a three-dimensional scenario talking about the orientation on a boundary curve, what does that even mean? I guess if you, and sometimes I've done this on tests, I've said, clockwise as seen from a particular point of view, or something like that. But anyway, it's certainly not good enough to set a standard. Here's the standard. The standard is, you start with your normal vector. You use your right hand, again with the right hand. Arbitrary. Totally arbitrary, full apologies to left-handed people. But arbitrarily it's the right hand, and you put your thumb in the direction of that normal vector. Right? Your thumb pointing in the direction of the normal vector. Now look at your fingers bending the way fingers want to bend. No hand yoga, right? No cheating, right? Bending the way that fingers want to bend. Again, your right hand. We'll define what I like to call a swirl. The swirl you're supposed to imagine as being kind of a little hurricane, like a little tornado of rotation that's going around that normal vector. And then we want to look at how that rotation, how does that sideswipe up against the boundary? And it will sideswipe up against the boundary in one direction, and that direction is the orientation. It's an arbitrary rule, right? But ends up being very convenient. Yes?
Does this depend on your choice of normal vector?
Oh, yeah, absolutely. Yeah, very much so. Yeah, so you can, play this game. Let's imagine that I have some surface like this, right? If the normal vector is up here, you can see the swirls are going one way. If the normal vector is pointed the other direction, you can see the swirls go the other way, and will give you the opposite orientation. Yeah.
Okay. So then is the point that the same normal vector that's used here to define the boundary or the orientation is also used later? So like provide consistency?
Yeah, so the point is that an oriented surface results then in a well-defined orientation on its boundary. And that's what we need, right? I need to know when you say boundary, I need to know what you're talking about in terms of orientations. And if the green is the orientation that was given on the surface, then you play this game, you look at swirls and side swipes. The resulting blue is what we mean by the boundary orientation. Yeah. Did I answer your question?
Yeah, so this is like the same normal vector that was defined before with the cross product.
Oh, yeah. Yes. Both of these are the same normal vectors used in the various kind of integrals we've talked about. Yeah. Okay. Looks like we're out of time, so see y'all later. Y'all have a great weekend. We'll see you on Tuesday.